By the way, we're going to calculate this fog vector in our skin C# class. I'll show you how that works after, but we're going to add that fog calculation into our vertex shader. We're going to return this vertex shader out. Let's change this to VS out, and that will be output to the pixel shader. And let's give this a more appropriate name for this vertex shader based on what it's for. I'm calling it vertex shader 3 lights skin, and we're going to use this vertex shader input, and I'm just going to call it vertex in, and that's this input format here matching up to our vertex declaration. So now we have this vertex out. It's going to hold our output information. We're going to create a function called skin. We'll put it above, passing in our input data, and this is in out, so it's passed in and it comes back here with the modified version of this bin data. So let's add that now so we can see that in action, so we know what we're dealing with for the rest of this method. So as you can see here, we allow up to 4 bones to influence a vertex. For example, if there was only 2 and we were adding this together, we take the weight of the first one, it could be 50%, and maybe the second one's 50%, adding up to a total of 1.0. So these would be 0.5 and 0.5, and this would be bone 0 and bone 1. And bone 3 and 4 would default as 0, but those weights would be also 0, so those would not factor in. So it still adds up to 100% though, because each one of these is 50%. Now if there were 4 actual bones influencing the vertex, maybe they could all be equally influencing also. Then these would be 0.25 for all 4, adding up to a total of 1.0. In a sense, we're interpolating the bone matrix for the vertex based on how much influence each bone should have. The reason why it's important for us to do this, I'll just give you a quick illustration. So let's say we're in the middle of an animation and we've recursed through the tree and gathered the animation for this much. So now we need the wrist here, and we need to rotate the wrist to here from the bind position and then add it on to the end here. Of course, inheriting some of these rotations, when we add it on to the end, it'll be more like this. We can't rotate it here, otherwise it'll do this sort of thing because it's trying to rotate around 0, because it already has a translation on it. And we got to do rotations first, translations come last. So we got to take this rotation off by using the inverse bind transform. So we use the matrix offset to get it into the bind position, and we use the inverse of that offset to get it down here. So we rotate it down here, and through the magic of matrices, by combining it with the parent, it'll add it on to the end here in exactly the way we want it. So now we'll have this here, and we can continue to recurse through the tree until we get the rest of the fingers. And they'll do the same thing and add on to here. But here's the thing. If I use 100% of this bone on these vertices and 100% of this bone on these vertices, you'll notice this is ripped apart here, and these kind of go inside each other over here. If I use 50% on vertices that are close to this joint, not on these ones back here, but just ones that are close to this joint, and these ones being close to this joint here, if these are weighted to be, say, 50% this bone, 50% that bone, as they go further back, those percentages get less and less because you want it to stretch out naturally. Then what you do is you use those weights, and because those weights are a little bit different, like they degrade as they go this way, you get this nice curved elbow as it bends. And that's what we're after. That's why we're doing this weighting thing. By the way, this unrolls the loop so that this actually isn't a loop. That's just an optimization. Okay, so here we can multiply our position by this resulting sort of interpolating matrix here, which has influence from both. In the case of the position, there's an X, Y, Z, and W component in the multiplication process of the skinning matrix. With the normal, the W component is not required. We cast it to a 3x3 float, a 3x3 matrix, and then we multiply it by the normal. We don't need to worry about the W component in that multiplication. So now going back to our vertex shader, our vertex input is now representing the transformed version of the position in normal. Now here I'm copying how Monogame did its fog calculation in their skin effect. We say fog factor is equal to the dot product between our transform position and the fog vector that's going to get passed in to the shader. It'll be calculated in the C# module. We use saturate to clamp it between 0 and 1. So now we have our fog intensity, essentially, which we're going to use in our shader below, our pixel shader. In fact, we're going to have that piggyback as the W in this float 4 here, and we'll keep the world position in the XYZ of the float 4 and pass all that through the world pose. So we have our transformed position of our vertex, but the character is not in world space, so we got to multiply where we want the character in the world. So we multiply that position by the world matrix to get it into the world position. We do the same thing with the normal, but in this case we're going to use the world inverse transpose in case there's any scaling. In this case we got all kinds of deformation of the character, so we definitely want to use that world inverse transpose to make sure that our normals are accurate. To explain why we use the world inverse transpose would take a while. It's kind of outside the scope of this tutorial, but you can look up that sort of thing on the internet if you're interested. And we normalize the result just to make sure that we still have normals of a length of 1, which we'll need to get accurate dot product calculations. So we'll use those normals with our lighting. And for the hardware, we get this position here. This will get the vertex into a position on the screen, essentially, by multiplying by the world view projection on this. Not on this one, that's already multiplied by world. So we're multiplying it on our original calculated position that we got from here. If we had passed in, for example, just view projection, then yeah, we could replace this here and put it here, and that would actually give you the correct result. And we'll just pass along our texture coordinate here, and then we can start our pixel shader. But while we're still thinking about vertex shaders, I'm going to add a vertex shader that'll prepare us for a normal map version. Okay, I got this normal map version here. Actually, I might just change the name of this a bit. And what you'll notice is that this is basically the same as before, except instead of vertex shader out, we're using vertex shader N out. We're using the output version, which includes this tan space in text chord 2. It's that float 3x3 tangent space. And we'll need that in our pixel shader. So we'll prep for that sort of thing. The other similarity you'll notice is we calculate our final vertex position so that it's in world space. We get the screen position, and we send the world position with the fog factor attached on the end, and we send the texture coordinate again. This time when we update our skin, we're going to have to take into account our tangent space. So we're going to make something called skin norms. Skin norms will be similar to our skin function. So let's add that after this. So what you'll notice is this is essentially exactly the same as this one. The only difference here is we're also multiplying the skinning matrix by the normal, tangent, and bitangent. In our case, I've been getting some problems with some of the bitangent data, so I'm just going to calculate it here down in our shader, and so I can probably just comment this out. But if you believe you're going to use the bitangent data and you're going to pass it in and just use it, then you don't have to calculate that and you can just keep that. I'm just going to comment it out. Later I may go back to and change the vertex declaration and also comment this out. For now I'm just going to leave it, it won't hurt. So yeah, I guess there's just this one extra instruction here for the tangent. We're going to pass along our tangent space matrix. 0 will contain the transformed tangent, 1 will contain the bitangent, and 2 will contain the normal. So to get our position into world space, we multiply by the world transform. In the case of our tangent, we're going to use the world inverse transpose. Same with the normal. And that's sort of the same thing we did up in this one, normal, for the same reason. Just to make this line a bit shorter, I said t is equal to this result that we calculated here. So then I can say t is equal to normalize t minus dot product of the tangent and the normal times n, normalizing it so it's a length of 1, and doing it this way orthogonalizes it to improve quality. And then we can calculate our bitangent by taking the cross product of this t and the n, which was our normal. And now we'll have a bitangent, the length 1, and we can assign that into tan space 1, and assign the normal n into tan space 2. So we got 0, 1, and 2. And we already went over this stuff, so let's continue to the pixel shader. This compute light will be shared, so I got that here, and some information will be passed in this kind of structure, diffuse and specular values. We'll get back up to this compute lights in just a moment. So let's go down to our pixel shader. We take in the interpolated value for the pixel as it's being interpolated between the three vertices of the triangle. And we'll sample color from our regular diffuse texture map using that UV coordinate and multiply it by the diffuse colorization, so the material color. In many cases, this might just be color white, in which case whatever is sampled here is going to be 100% of the red, green, and blue channels. If, for example, the diffuse color had a green and blue channel that were, say, 0.5, then the green and blue here would become half of what was sampled, making this sort of a redder tint. Of course, that depends on what color was sampled here. So we're going to need a few vectors to make our lighting calculation. We'll need the vector that points from the surface at this position on the surface, which is here, to the camera. So we go camera position minus this point on the surface, which we're interpolating here. And we normalize that vector so that it's a length of 1, a unit vector. And because we're using unit vectors, we can use the dot product with those, for example. And we can use the dot product to figure out how different those angles are to sort of scale the intensity. Now in this version, we're not using normal mapping. We're going to make another one that does use normal mapping. So we're just going to use the regular interpolated normal and normalize it, store it in here. And we'll use compute lights, which we have up there above, passing in the normal and the I vector and telling it that we're going to use all three lights. So continuing, we got our I vector now and our normal. So each one of these is a float 3, the light direction, light diffuse, light specular, half vector, and we'd go 1, 2, for example, 3 for each one of those. But instead of doing that, we're going to say float 3 by 3, so we got 3 of each of these. And that way we can just loop through the lights for all 3 of them and use I as an index here. And by putting this unroll here, it should unroll this loop and optimize it. So by casting this to a float 3 by 3 and then using the index here, it's just a clever way of selecting, like if this is 1, for example, if it's 0, it's going to select this one. If it's 1, it's going to select this one. So which one this equals to is just going to depend on which part of the loop it's in. Same for each one of these. Oh, by the way, this is a bug here. Instead of 3, this should say num lights, because we might decide to make versions of the shader that are only doing 2 lights or whatever. If you put these 2 directional vectors tail to tail, or head to tail or whatever, and you normalize that, you get a vector that's kind of in between the direction toward the camera and the direction toward the light. So we call that the half vector. So this is a point on the surface here. We got this vector, length 1, headed in the direction of the eye, or the camera, and another one, pretending this is length 1, headed towards the light source. Half vector is more or less in between. 3 by 3 is like a 3 by 3 matrix essentially. So we can do like something like a matrix multiplication here, where we multiply our normal that we passed in by the light directions. And that'll affect all of the ones we have. The ones we don't have will probably be just a row of zeros. And the result will be stored in this float 3. So it'll be 3 sort of like angular differences between the light and the normal. And we do the dot product for the half vectors versus the normal to find out what kind of difference we have here in the angles of those directional vectors. So if we got 3 lights here, which we most definitely will for this example, we're going to end up with 3 floats representing each of the half vector difference, how different the normal vector is from each of the half vectors. I'm using this step here with this float 3, the 3 zeros here against dot L to make sure that none of those entries are less than 0, essentially. And here we're calculating our 3 diffuse light values by getting those clamped version of the dot L. I've never actually seen how or where they come up with this math, but what this looks like to me is almost like they're trying to square the dot L, but they want to reserve the sign value. So if this was negative and you squared it, you'd get a positive, but you might want it to still be negative. So maybe that's why it's like this. So then we get our 3 diffuse intensities here. On a side note, if you do find this math to be a bit confusing and you just want to use a simpler Phong lighting or half vector lighting example somewhere and maybe just 1 light, or add the 3 lights in separately with kind of less fancy operations here, you could do that. There's plenty of examples on YouTube. There's ones too for setting them up. DirectX shaders to use with 3D Studio, and those can actually be used in pretty much exactly the same way in this sort of thing. For our 3 specular values, we use this max here just to make sure that we're using a value that's greater than 0. And we multiply the .h, the half vector value, by the intensity that we got for by how much difference there is between the normal and the light's direction. And we raise that to the power of specular power, which is another uniform value that we pass in. And using this color pair structure up here, we can pass along our 3 diffuse intensity values and our 3 specular values. First, we got to calculate what those final diffuse and specular values are. So we multiply our 3 light diffuses. So yeah, basically our 3 light colors by the 3 corresponding diffuse intensities are multiplied together, and then we multiply that by the diffuse color for the material, and we add the emissive color, which also contains our ambient factor. So this would contain our minimum amount of light that we would expect to have coming from the diffuse color. And for the specular value, that's that sort of reflective shine that's coming off of the material. We do the same sort of thing. We use the specular intensity against the specular light colors and multiply it by the final specular. That's the specular color that we expect to reflect off of this particular type of material. And then we can return the result in a color pair. And before we had sampled our color out of our texture up here, kind of scaling it by the diffuse color of the material, which is probably going to be 100%. And we can now multiply that by the diffuse lighting on the material from the lights, from each of the lights. So this will multiply this color value by all 3 of those, thus allowing all 3 directional lights to influence the intensity of light on the material. And that's that scattered diffuse lighting that you see on the regular lighting on the surface. The specular is a bit different. That's sort of that reflective shine. Just ignore this part here for now. So this is just something I added that's extra for the eyes. The next thing we can do is add in the specular effect. This will amplify the brightness depending on how much specular there is, and by those specular colors. This will take all 3 of those specular values, multiply them by the shine amplify, which is an extra thing that I added. Normally this actually would be something like this. This results in the same sort of thing, but it allows me to get a little bit more control so I can add that extra shine with the eyes. And I'm sort of adding some extra stuff here to help out with the shine on the eyes. So if the alpha value of the sampled color is below 0.8, I have the material set so that the alpha will be less than 0.8 if it's the shell that goes over top of the eyes. And I say red greater than 0.8 just to check to make sure that there actually is a material color to it. It's sort of a way to identify that it's the eyes that we're dealing with here. This is for amplifying the shine on the eyes and otherwise ignoring the shell material of the see-through shell material on the eyes. I don't remember exactly what I was doing, but I can tell you that you can ignore this and ignore this part, and what you would normally have is times color.alpha. So we're adding that specular shine to the resulting color that we calculated here. And this is more or less the same thing, except it works with whatever I was doing to boost up the shine on the shells of the eye surface. So under that, we have this fog vector.w greater than 0, meaning there is a valid fog vector that we can use, or the fog is being used. We know that from this. We can do a linear interpolation between the fog color and a resulting color on the character. So if it's really far away, using this world position.w, and that was our fog vector calculation that we made in our vertex shader. We put the fog vector in the w component and passed it into world position. So you can just pretend this doesn't say world position, this is just the fog factor value. And we're using that to interpolate between our color value and the fog and the distance, depending on how deep we're sampling into 3D space. For a moment there, we were actually looking at the wrong version of this. So just in case you got confused and you see normal map calculations up here, that's because we were looking at the wrong one for a second there. And I just got to clean up that other one, and we'll add that next. Alright, this is the normal mapped version, and what's different here is we're getting our normals from a normal map instead of interpolating across the surface to get our normal. The problem is the normals on the surface are represented in their own sort of space, where the arrows are kind of pointing away from the surface, and we need it relative to the triangle that we're working on. So it has to be where that triangle is kind of, or I should say it has to be pointed in the right direction, so that's the same direction that the triangle is pointing. Also, we got to keep in mind that our vectors for the normals can point in any direction, so they can be pointing in a negative x, negative y, negative z, positive x, y, or z, and the colors, red being x, green being y, and blue being z, are represented as 0 to 1. So we got to convert that by either multiplying by 2 and subtracting 1, so it ranges from -1 to +1, or what we can do is we can just take the color value and subtract half of it. So if it was at 0.1, it now becomes -0.4, for example. So we're going to subtract 0.5 from each of those entries, and by normalizing it, it's going to make it a length of 1. And now these little vectors will be pointing in the appropriate direction. It could be negative, positive, and they'll all result in a total length of 1. So that's the normal color variable here, which is technically now a vector, but we need that vector in our tangent space, and we calculated our tangent space up here such that we got the normal and the tangent multiplied by our skinning matrix, and then down here we use the world inverse transform, which is basically like multiplying it by the world transform. We're using the world inverse transform to avoid any complications with scaling. So we do that with our tangent space 1 and normalize it. We reorthogonalize and calculate the bitangent, and that's stored in the second one. The bitangent will align, I think, with the V, and the tangent will align with the U, and our normals will point outward. So this matrix now essentially will take any of the normals we take off of the normal map, and when we multiply against those using this matrix, it'll get it so that it's relative to that triangle on that character after animation, and where the character is, and what direction the character is facing. So then all we do is multiply by the matrix to get the coordinate in the tangent space. And now we have the proper normal as though those normals were represented along that part of the surface. And we normalize it to a length of 1. And then we can use that as our normal like we were before in our calculations. And as you can see, everything else is identical to what it was up here. So a brief explanation as to what this tangent space thing is, why we're using a tangent space matrix to get our normal map so that these normals are facing relative to the surface. Let's say, for example, we got this lid handle and we want it to have some bumpiness for some strange reason. And we got a texture that we're wrapping around it that contains a normal map. And each color of the normal map represents the direction that the normal should be facing, so that the light is calculated slightly differently for each texel or pixel or fragment, depending on how you want to say it. For each pixel on the surface, there's going to be different lighting value. And it kind of creates that 3D bumpy illusion where the lighting looks different. And it's good for dynamic lights too, because if you move the light around, lighting and shadow changes. So here we have our normal map, or we'll pretend this is a normal map. And each one of these pixels on the normal map, obviously these are going to be much smaller and there's going to be much more of them, but for this example, let's just pretend this is a very small normal map and we've zoomed into it very close and we can see each pixel. And each one of these has a red, green, blue component to its color. The red component represents how much it should be rotated in the X direction, and the green component is going to determine how much it should be rotated in the Y direction, which is going to be up and down. Our coordinate system's different. Y would actually be up and down here. So Y is where Z is where Y is. As far as Z goes, they're all pointed outward in this direction. Again, just pretend this is Z. And This one you could imagine would be partly green because it's pointed kind of upward, but it's got some blue to it too. All of these should have a certain amount of blue to it. So it'd be kind of a greenish blue. And this one is kind of pointing to the right, so it would kind of have a reddish blue, so sort of a purple. This one's kind of pointing down and to the left, so the red would be decreased, making it a darker blue. The green would also be decreased, making it even darker yet, to indicate that it's pointing in this down direction. If we take the red, green, blue value, of course you can imagine that these little arrows are on every single one of these, and they're all pointing in different directions. I just drew 3 of them just for examples. So if you take the red, green, blue value here, it's going to range from 0 to 1 for each channel. But we need to know the direction ranging from -1 to +1. So we can multiply this by 2 and then subtract 1, and that'll give us the range value between -1 and +1. That way for this one, the red value, for example, should be pointing left, but it's going to instead be something like 0.2. If we subtract 0.5 and then normalize, we get that negative value. So this would be like -0.8 or something. The other way to do it is to multiply it by 2, in which case you get 0.4 and then subtract 1, and in that case actually you get -0.6. So this is pointing -0.6 in this direction. So that's how you decode those colors into the directions they're going. The problem is this is all relative to this normal map, which sits along the x-axis for the u direction and the y-axis for the v direction, and the z values of these normals would be pointing along this z direction here. So how do we get this so that it's relative to the surface position that we're trying to sample? We have that tangent space matrix, and basically what it does, first of all, one of the things you're probably aware of is it's multiplied by the world matrix, or the world inverse transpose in our case, so that we're just dealing with directions, so that it's oriented correctly relative to the object. However, it might not be relative to the surface. So each time the vertex shader does an update for the vertex, it creates that tangent space matrix so that we have a version of this that works relative to the vertices, and thus when we sample our per pixel lighting in the pixel shader, it's going to be having directions that are actually relative to the polygon that we're sampling from. For example, there may be a position on the top of the surface here, and it would be sampling from, say, one of these little pixels. Well, you'd have to imagine that these are much smaller. And then using that to get the normal for that sort of bumpy spot on the texture. And then we use that normal in the lighting calculation. For a different part of the object as it goes through the vertex shader, it's doing different calculations against it to get it relative to the surface, and then again when it samples, it's going to be sampling from the correct part of our normal map. And keep in mind what it's doing is it's aligning the X and Y values on our normal map with the UVs of the texture map that's used on this. And it's as though it's aligning our UV surface with the polygon that we're working on at that moment. And that way each one of these is sort of an offset from the normal on that polygon. So we can take the new normal that's calculated and just use that in our lighting calculation. If, for example, we want to align it to this polygon here that I'm kind of circling, for this vertex, this is sort of your tangent here, and that's going to be the u direction of our u coordinates, and our v direction is going to go running along our bitangent here, and the normal will face out this way. So we use that matrix to get it so that it's lined up to this. And again, the UV values determine where we're sampling from. So we'll multiply by that tan space matrix, and you can imagine that it's lined up appropriately to that polygon. Something kind of like that. So that sums up our shaders. We could do a few different types of pixel shaders, vertex shaders for handling different situations, but this will be sufficient for my purposes. So I'm just going to do the normal map version of the shader and the regular pixel shader for when I'm not using normal mapping. Let's go down to our technique. If we make a bunch of different shaders that we can choose from, maybe certain ones do not include fog, we can have our program select the appropriate technique based on booleans or whatever set up. I'm going to add a definition here that'll make it a little easier to set up our techniques. we got this definition that we can use here, sort of a macro. If I wanted to do something like this, for example, where it says name, I'd give it this, basic color drawing. The S name would be the vertex shader's name right here, the method name, which would be substituted here. And same idea for the pixel shader, main PS would go in here and would be used here. So let's use this and change up our techniques. So when we want to select a technique and apply it, we may want to write these down. In our program, we're going to use these names to select which technique we want to use. So this one is just regular, and this one is with normal maps. And you want to make sure your vertex shader method up here, make sure that name matches. You might want to just copy it and paste it to be sure. And same with your pixel shaders. And that's it for the shader. So we can save our shader now, and we'll go over to project and right click for the folder skin models. We'll right click and add class. I'm going to call it SkinFx. I'll just say effects like that. Starting at the top, we'll add a helper class. Okay, so we got our directional light here. If you want, you can call it directional. That's usually what we refer to it as. And if we had point lights or something, if we wanted to add that, we could set up point light ones too. And those would have radius and attenuation and such. By the way, in the skin effects, when we set the max bones to 180, if you really wanted, you could make it much higher, maybe 500, maybe even 1,000. The most number of bones I've ever needed for a character was 150. So I just added on a little extra, made it 180, just as padding sort of. But I mean, you can go and change this anytime as long as you remember to change that constant in here as well as elsewhere. So back in our skin effects, I add these constants here, making sure that this matches. And we're processing it for up to 4 vertex weights. We'd have to change our formatting if we wanted to change this for the vertex format. So the number of weights per vertex doesn't have to be 4, but it has to be 4 or less. As I mentioned before, the ones that aren't used are just going to be added as zeros and not factored in. We're going to need a reference to our camera so we can pass along that viewing matrix to the effect, and we're going to need the effect that we're going to use. If we want, we can set a default texture. It could be that plain gray or checker pattern for debugging, but unless we're debugging, we're probably not going to use the default texture. Probably just use the textures that are attached to the character. If there's a missing texture, you're going to notice that it'll be gray because it'll end up using the default texture. Or perhaps not gray, it may actually be the diffuse color of the material. So here we actually have our material properties, and diffuse color can have an alpha, so we use vector 4 for that one. And emissive color has no alpha, specular color has no alpha. Those are just the color values. There's no emission by default, so it'll just be the regular diffuse color. And the ambient will be added on. Ambient is also 0 by default, but we'll be getting the material properties from the file, so it'll just add those material properties into here in place of these. Specular color by default is light yellow. I use this 2 vector 3 here to change the color to vector 3. Specular power is 32, just as a default. And we've got an array of directional light, and we're going to use 3 directional light sources. There'll be one primary one and sort of 2 support lights. So a key light, a fill light, and a backlight, depending on how we handle those lights. Default alpha is 1F, so that's going to be opaque. Got our fog start, our fog end, our world matrix. The world view matrix is the 2 combined. No perspective projection. We just need to use this for getting our fog vector. I'm going to show that later. Now let's move down to our constructor. In here we're going to load the default texture. So I passed in the content manager. We're going to want to reference the camera. So any changes happening to the camera, it's going to be updated and we have access to it. We're going to want the file name for the effects for whatever effect is going to be associated with this by default, and initially whether or not we're going to enable fog. So here we're just allocating our 3 directional lights, creating 3 new ones, setting that reference to the camera, loading in our effects based on the name that we passed in here, and loading our default texture, which is going to be default texture in our content folder, which I believe we already added that. So just make sure that name matches up here. Now, we don't have this set bone transforms yet. I'll show you that in a moment. We're just going to be initializing so that all of the bones are going to be matrix.identity by default. And in the constructor by default, we're just setting the diffuse texture to default texture and passing along the colors, the default colors that we set up here. Now, these will all most likely be changed anyway, but better to be safe. And then we're going to set the default lighting, which we haven't made that yet. I'll show you that in a second. And we'll also toggle the fog on or off depending on what this value is here. So if that's true, then it's going to use this. Okay, and I added this. Set bone transforms, which we use to initialize our bones to be identity matrix. And that's just with this temporary array for setting it up. This part right here, just make sure it's not null, make sure it's not 0, make sure it's not too many bone transforms being passed. And then we set the bone transforms being passed in to the bones array on the graphics card in our effects file. And you want to set your ambient color usually to be something fairly dark. In this case, there's a little bit of extra blue here compared to the red and green channel. I'm not sure how I got these colors. I might have used a converter. Same with these directional values. These seem very specific, so not sure what I did for those. This is our default diffuse color, default specular, just some defaults for each light. You can play around with those. The fill light's not doing any kind of specular, so we put the fill color to vector 3.0. For the key light, obviously we want that to shine, so we give it a good value. It's fairly high. And the specular color for the backlight, we keep it pretty low. Same with the diffuse color. And then we just set those values on the graphics card. And this will only be done once in the constructor. So that's just our default lights, but we're going to be wanting to set some of our lights on the fly at times. So let's set something up to pass in parameters for each directional light. Here we can pass in the index of the light we want to set, the direction, the diffuse color, and specular color. Make sure the index is valid, and we set that direction in our light by index. And we do the same for color, have to cast it to use this .2 vector 3, and same with the specular color. Then we can switch for the index to pass those into the appropriate parameters. Now going back up here, we're also missing the toggle fog. So if this is true, we want to turn on our fog. So let's go down here and add that. Initially, fog is not enabled, so that'll allow us to jump straight into here. And if we wanted to change something about our fog, we can make the changes we want, and then just remember to set this fog enabled to be false, and then call toggle fog. And then that way it'll make sure it executes this code here. And it'll only do it once. And I'm not 100% sure how this fog code works here. I know what we're kind of doing is trying to figure out how far away each pixel is in the pixel shader and use that to determine how much fog should be added. How exactly this version works, I'm not sure. This is with the skin effect that came with Monogame. This would probably never happen, start and end being the same. We're calculating our fog on a per vertex basis here. We gotta transform our positions into view space and take that depth value, that resulting Z, and scale that based on the starting and ending distances for the fog that we've set. Now the part that I'm not really sure about is it says here, because we only care about the Z component, the shader can do all of this with a single dot product, using only the zero of the worldview matrix. So first of all, we subtract our start and end, and we say 1 divided that amount to get how much to scale it by. Obviously, if these values are the same, this would be 0, and that's why we have this line up here. So then we can take the 0 in the worldview matrix and scale it, and we'll place that result into our fog vector. And for the W component, we have this offset, this fog start added on, and then we pass that into the shader, into fog vector. And if you look in the shader, we can see that the fog factor is calculated using the dot product between this vertex position and the fog vector that we calculated. Like I said, I'm not 100% sure how that works, but I know that that gives us our fog factor or intensity of fog based on distance, and we're saturating to clamp it between 0 and 1. And now fog enabled is true, so we've already done this, we don't need to do it again. If we get here and fog enabled is already true, then it'll do this, because we're disabling the fog now. So fog vector becomes vector.0, and then we say fog enabled is false. And if we make a non-fog vertex shader and pixel shader, we can actually check the fog enabled and just have versions that don't do anything with the fog vector and that. During our code, we may want to change some of these fog values for whatever reason. Maybe we're going into a new area where the fog is going to be a bit thicker. Let's add some ways to set those parameters up above this toggle fog thing. We can set the fog start, the close part of the fog, set fog enabled to false, so it'll actually run this code in here, and then set the fog start value so that when we call toggle fog, since this is false, it's going to go through here and it's going to calculate this with a different fog start value. And we do the same sort of thing for fog end, that's the further end of the fog. And for setting the color, we can just directly set the parameter here. Fog color is equal to .set value, fog color .toVector3. And we're just going to make sure that this matches up in our shader. Another thing that could change as we're looping through our characters' different body parts, there may be a shirt, they may be hair, different types of materials, different textures may be used, plus also the camera will be updated each frame. So we'll need a way to change those drawing parameters. Down below the toggle fog, I added this set draw params. It's used just before drawing. We can set the camera, we can pass in a custom texture. So if the texture is null, then it'll use whatever the default texture is, which you can see right here. If the normal map is null, so first of all, we can multiply our world and view matrix together to get that world view matrix that we use in our fog calculation here. We're going to need the world inverse transpose to get our normals transformed correctly in world space. To get the world transpose, we use the matrix.invert on our world. And then to get the actual transpose, we say .transpose, world transpose, and then we have our world inverse transpose. And that doesn't make much sense. This should actually say inverse, not transpose. So let's change that. And we'll change it here, and we'll change it here. If it was just a static scene, we could just use the world transform on our normals, but since this is an animated mesh, in order for those normals to be accurate, we have to use the world inverse transpose. If you want to look that up online, world inverse transpose and normals, you'll find out why that's done and how it's derived, if you're interested. So we got this alpha value up here, so we can control the transparency of the material, and we can set that outside of the draw params too if we want, because it is public. And that is used against our calculation for our diffuse here, as well as our emissive, which kind of holds our ambience too. And as you may remember, these are the material properties. When we load our FBX, we're gonna have material properties that we can set during the loop. And by setting diffuse W to alpha, we can send in our alpha amount. Emissive will usually be 0. If we wanted to look a little bit like a cartoon, we could brighten the emissive properties. Also too, if we had a light coming out of it, like a light positioned inside the material, we could boost the emissive properties of that material to make it look like it's actually shining. Without the light in it though, all it's going to do is brighten it. And we're using our ambient values to scale our diffuse here. So you probably want to keep your ambient pretty low. Keep in mind too, we pre-multiplied our diffuse colors here. And we send in our world transform matrix and our world view projection matrix, which puts our coordinates into a perspective on the screen. And we send in the camera position, which is going to set up that eye vector for doing the lighting calculations. If there is a diffuse texture, it'll use that, and if there isn't one, it'll just use the default texture. And we'll only set the specular texture if there is one. So if some of your characters have specular textures on them, you might want to comment this out for now to make sure that it doesn't try to set to text specular, because what's going to happen is in our effect, when it compiles it, it's going to see that we're not actually using this spec sampler, so we're not actually using this text specular, and what'll happen is it'll optimize this out. So this won't even be in the final version after it compiles it. It'll only keep this if we actually use it. So if we made a version down here, or just added it, in fact, I'd probably just add it. I mean, we could even put a Boolean at the top that we can pass in to indicate that the specular is being used. Or we could just have it select a different technique if specular is there. And that way we'd have code that supports the specular sampling. So we'd have to have a specular sampling kind of like this, like we did with the diffuse color, or the normal, normal right here. Except we'd have to have something with specular and then use that. We could probably sample the specular and just add it as another scalar here, like text spec samp or something. And that would add some extra scaling factor to this specular here based on the specular texture map. But like I said though, since it's not in here, the specular sampler or the specular texture will be optimized out. And so passing this in could result in a null exception error, and it might not necessarily show up here. So something to keep in mind. Once we've added the specular mapping support to the shader though, of course we can go back here and we can uncomment this. I think I'll leave that commented for now, just to be safe. And for the sake of our normals, we'll pass in the world inverse transpose, and we'll pass in our diffuse color and emissive color, which we calculated up here, and those are for the material. If we're not using normal mapping, we'll set the technique to this skin 3 lights. And if we are using it, then we can set the value for the normal map and make sure we use the correct technique. I think I actually changed the name of these, so I'm going to go back into the skin effect and copy those names out to here. Yeah, so let's copy this one and paste that here, and then we'll do the same for this one. I just thought directional lights gives it that distinction from the point ones if we make point light versions. We could also have a number of directional lights and a number of point lights, and it could just use the number of them to decide how to process it in the shader. That way, obviously, if there's 0 point lights, it's just going to use the directional lights. And we may want to just modify a few values. So let's add some other extra parameter modification stuff down below. So we got set diffuse color, set emissive color, set specular color. In the case of emissive and diffuse, as long as we just assign them, that's good enough, because we're going to be calling this set draw parameters every frame anyway, just before the draw. And so those are going to get set up here, right here. As far as specular and power goes, we're going to set those right away after we set it here. We're going to set it into the shader as well as specular color and specular power. Make sure these are the same in your shader. In the case of set shine amplify, I'm not storing that value in here, so I'm just going to directly pass in the shine amplify value, which I'm just using for the eyes. And that's it for SkinFx.cs. All the drawing and stuff we're going to do elsewhere. So going back to the SkinModel class, we can uncomment this SkinFx now, because we have a SkinFx. And let's go down to our draw and kind of see what's happening there. So let's find draw, and the draw method we'll use the most will probably be this draw mesh, so that as it loops through the meshes, we can change the material properties and settings based on what it is. We'll be using the mesh materials. Actually, we might not. I think we'll actually set our own, but if we use them, it sets those here, and it's just directly changing those values. But we'll probably send our own values directly into the SkinFx itself. Oh yes, and I notice here we're setting the specular, but we're not actually going like this, like set specular color, specular power. So we'd probably want to use those to make sure that it's updating those values on the device. Like I said, I'm going to be doing that directly, so I'm not too worried about that. We'll set the draw parameters for the diffuse texture map, the normal map, specular texture map, we're ignoring that for now, but we can have that passed in and add the supporting code for that later. Since those are set, when we draw it, everything should be okay for that particular part of the character. At this point, we have everything we need to store the data of our skin model and to animate and draw the skin model. But what we need is to be able to load an FBX file. Based on Wil Motil's efforts, we're going to start our skin model loader. So let's go to our skin models folder and we'll right click and add a class, and I'll call it skin model loader. So as with skin model, we want this defined using colored vertices. We'll copy that over. So if we did feel like including the colored vertices, we got this definition here, and we can add supporting code for colored vertices. In my case, I'm just going to let the texturing take care of the coloring of the polygons. We're also going to need Assimp and Assimp configs. So I got those up here. And I again added the instructions for setting up AssimpNet, the open asset import library, which we're using to load our animated FBX. The first part I added is just a list of booleans that we can modify if we need to do any kind of intense debugging of any file loading if the file loading isn't working right. Most of this you'll probably never use. I'm just including it just in case for whatever reason you decide you want to debug something. I'm going to leave file path debug to be true and minimal info to be true. A lot of the debug information stuff, I'm just going to kind of skim over it and skim over the support methods for that as well. I'm not going to go into too much detail on that because, like I said, that's just for debugging purposes, for doing diagnostics on what's happening during the loading process. So I'm going to minimize this region here. Next up, we got this members region. So as usual, we got a reference to our device. We got a scene here. Just had to pause the video for a second. My recording software had a memory leak and it seemed to be causing issues for my IDE. So back to what we were working with here. We're adding some members that we're going to need. Graphics device, we can right click that, do the usual to add the usings. So this will be the file name without the extension, a possible alternative directory to look in. If you're wondering about the scene thing here, as long as you have that Assimp package, which you should by now, when you hover over this, you should see it says class Assimp.scene. So when we load our scene, this is basically the thing that holds everything that's in that scene. So our character and whatever else might be in there, preferably just our character. So this is based off of a version that I was already working on. And I just realized something. We got this use debug text and debug text. And within this model loader, we actually assign the model's texture to these, or the model's debug texture to this value. So if we look in our skin model, we've got debug text and use debug text here, but we're not actually using it. I'm going to leave it there though, just in case we do want to use it for debugging, but we'd have to create a method that does use it. We might even want to add support for it in something like mesh debug draw, just to make sure our UV coordinates look good, or draw mesh by name, so we can just pick which mesh we want by name and draw it with the debug texture to see how the UV coordinates are turning out. So I'll leave that up to you. If you don't ever think you're going to use it, I mean, you could always take this out or add it in again later, and same thing too with the loader, but just for completeness, I'm going to keep it in the loader and keep this here for now. So yeah, like I said, if you don't think you're ever going to use this debug stuff, each time you see this debug texture, Boolean and texture, I'll leave it up to you. You can take it out if you want to. Load debug info, that we're going to use with these settings here. And it's just going to do a display. It's going to put stuff in our output console here, providing diagnostic information about what's going on in the file load. This class we're going to put in another folder. So let's go to our skin models folder and right click on it and go new folder. Gotta rename that. We'll call this skin model helpers. And then on that, I'm going to right click and add the load debug info class. Load debug info. We're going to be using Assimp system.link, And this is going to be pretty crazy, so I'm just going to kind of skim over it. You may have to pause it if you're copying it that way. And there's also going to be source code available. In our constructor, we're going to pass in the instance of our SkinModel loader, and then we'll keep a reference of it stored here in this LD thing, which is nice and short. We got this write header to write to our console window a header message. Right after that, I got this console Assimp output region, and there's a lot of messages in here for debugging purposes, depending on which booleans are set. So we got the Assimp scene dump. We can provide the scene, and it'll just dump information out about that scene. And if we don't have the boolean set to provide any of that information, it'll just return. In our scene information, we got the model name, camera count, light count, probably won't have any cameras or lights, mesh count, material count, texture count. In this case, I think is embedded textures, which we could provide support for later if we wanted. How many animations, the root node name, all the light data, their names, cameras, camera data, and we got our meshes. And we loop through the meshes, name, vertex count, face count, normals, tangents, bitangents, depending on whether that information's in there. I mean, if it's not, it'll say 0. And we can loop through our texture coordinate channels. So we got that info there. And we got our bone count, looping through our bones. As you can see here, we can get information about the name of each bone, the vertex weight count. And at this point, you may be wondering how it's storing some of the data. This seems a little bit unusual. So down to the material diagnostics, we can check our diffuse color, specular color, reflective, transparent properties, shininess, shininess strength, in which case I think that's shine and glossiness in 3D Studio. We can have other properties like reflectivity, shading mode, blend mode, the scale of our bump mapping, so how much effect the normal map should have on the surface, if we actually want to use that. Like a lot of these properties, we probably wouldn't have to check it, but everything's here if you want to. You can even go through the source code and prune anything out of the diagnostics if you feel like you don't need it. And there's other stuff here showing like if it has an opacity texture or reflection texture. And we can get information about our textures here too. We can loop through and display which index it is. And we can use our loader's get file name to get the texture's name. We haven't made that yet, but as soon as we go back to the loader, we're probably going to add that right away. This, I believe, is the original file path, and some other properties, texture type, operation, blend factor, UV index. We might be a little bit more interested in the animation information. We're going to loop through our animations, providing the index and the total number, the name of the animation, and then we'll loop through the animation channels, getting a node animation list for each channel and displaying its node name. And we can use this get Assimp tree node, passing in the scene root node, the node name, and outputting from that our node information, which is going to be stored in this node type. So what that does is that calls this method down here, get Assimp tree node. So we passed it in our root node, the name, and we're going to output the node. So in each recursive iteration, if the tree node name is equal to the name we're looking for, we can say found is true, and we can set the node to be equal to this tree node that got passed in. Otherwise, we do our recursive looping, and we go through all of the children of this tree node, and we say found is equal to get Assimp tree node, doing the same thing basically, passing in each child in n as our tree node, and passing in the name we're looking for, and waiting to get that node. If nowhere in the recursion does it reach this point where it's found it, obviously this is going to stay false, and it'll just return false. Otherwise, it'll return true, and it'll output here that node that we're looking for. So if that node is a mesh, has mesh indices, we're going to say has meshes, and then provide the index count here. And if it's a bone node, then it's not going to say has meshes. However, for each of the mesh nodes, it's going to supply that mesh's name. So in this case, we're going to become aware if we have some mesh animation nodes. And this method here is actually here. Assimp node hierarchy dump does exactly what it says. Starting at the root node, we can go through recursively to get information about the entire tree. We're using 0 spaces here. That's just how much indenting to do. Here we're saying what the node's name is, whether it has meshes, mesh count, how many children it has, and the indice count. And we can provide information about the index of the mesh and its name. And we loop through the children, and we recursively call this, and we're adding 1 space for each layer of the tree. So it indents it a little bit for each layer, so for each of the children. So also have this region console model output. Got this method here, display info, passing in the model and file path, and here's where we have our switch booleans coming into effect to determine what we want to display. Now again, we don't have this get file name yet in our loader, but we're going to have that soon. So here we can show the file name, the file path, looping through our animations here. We can show the name of the animation, the duration, and we can show total duration in seconds. We also got the counts for node animations and mesh animations and morphs, although we're not going to be using those here. And this will also display the node hierarchy as well as the mesh and materials using the 2 methods that I'll show you below. And if we have boolean set for minimal info or for load model info, then we'll show the minimal info. That'll also be below. Right now I have minimal info turned on as true. So up here we're getting the node hierarchy displayed by calling this here, providing the model and the root node. We can show the node name, the number of children, whether or not it is actually the root bone, otherwise what the parent's name is, whether it has a real bone, if it is a mesh node, and we can check our unique mesh bones list here. And we can check how many there are, we can check the node name, the index of the unique mesh bone, and what mesh it refers to, and the index of the bone it refers to. And this big line here is getting the name, showing the name basically of the bone that refers to. And finally the name of the mesh that is being referred to. And for each of these unique bones, we're also going to check through our animations and the animation nodes. When we find a match to an animation node, we can show which animation is corresponding to that unique bone. And so we can call upon the children recursively and sort of do the same thing until we've gone through the entire tree. That's this method here, info model node. You may notice here too we call upon something called info for mesh materials. I've got that further down. I'm going to come back to this one, info for anim data. I'm going to skip that for now. Down below that, we've got this info for mesh materials, taking in our model and our original Assimp scene data. As you can see here, it says each mesh has a listing of bones that apply to it. This is just a reference to the bone. Each mesh has a corresponding offset matrix for that bone. And that's important because you could have 2 different sets of skin meshes. This means that offsets are not common across meshes, but bones can be. So basically, each skin mesh can have different offsets, even though they're using the same bones. And this is if you're dealing with attached skin meshes, like if you have a head that's separate from the body, for example, i.e. the same bone node may apply to different meshes, but that same bone will have a different application offset per mesh. And each mesh also has a corresponding bone weight per mesh. So this is just something important to keep in mind if you're trying to understand some of this. Let's just get our information here for diagnostic purposes. We're going to loop through the scene meshes. That's the Assimp scene. We're just saying the mesh's name, face count, vertex count, normal count, bone count, material index, morph method. We're not going to be using morphs though. Has mesh animation attachments, which it very well could. And here we got all our UV coordinate or texture coordinate information. I'm just using the same UV coordinates for the normal maps and everything else. If there are embedded textures, we can provide information about that here. Otherwise, we can say embedded textures none. And here we go over the materials, material index, the material's name, how many textures, and we can display some useful information about the textures, its index, what type it is, operation, and the file path. And for each material property, we can output information about ambient and diffuse and so on. We'll just scroll over to the right here. So we have these booleans that say whether or not there's, for example, diffuse color or has color transparent, so on and so forth. So just status of the material, reflectivity, two-sided or not. Some of this information could be useful depending on what you're trying to do. But again, this is just for diagnostics, so it's a good way to inspect all the information that's come in from the file. Now, if there was no materials present, it would say that here. Here we're going to loop through the meshes, showing the index and name of the mesh we're looking at. If it has bones, we say how many bones it has, and we loop through those. We can provide information there about the name of the mesh, the name of the bone, Assimp mesh bone index, the weight count. Okay, that's that. So back up in our display info, you may remember that we also had this minimal info thing here. So again, I'm going to skip over this info for anim data for now, and we'll go down here, and we got this minimal info here. So this is probably the only thing we're really going to have turned on. We'll show the file name of the model, we'll show the model's root node and its name, we'll show the number of animations, we'll show the number of meshes, and then for each of the meshes we'll show the mesh number, the name of the mesh, the material index name, or the material name, the bone count, the regular texture's name or diffuse texture name, normal map name, provided there is one, and if later we add height maps or other types of maps, maybe reflective maps, specular maps, we can add all that information in here too. Like I said, this is minimal info for debugging purposes. Okay, so we're back up to that one we skipped. Info for animation data. We're going to loop through the Assimp animations, and a lot of this, it'll depend on whether console info is set to true as to whether it's going to show it or not. So we get the time duration of the animation, has animation status, how many animation channels there are. We can loop through the animation channels and provide the channel mesh name, has mesh keys, mesh key count, and we can loop through our morph animation channels, get information about that if we happen to have morph data for some reason, whether it has node animations and the node animation channel count. And for each of them, we've got position keys, rotation keys, scaling keys. So how many of each of those for the current channel we're looking at. Then we loop through our node animation channels. So we got our animation node here. So just for the moment, I separated this into two lines. Got our node name and the total duration in seconds calculated here. So I'm just going to backspace that there. Then we got our position key count. So here we loop through the position keys, getting information about the timing and the actual position value. So we'll add an extensions helper in the SkinModel helpers, and we'll add this thing in there. So don't worry about that for now, we'll add that. And we do the same sort of thing with the quaternion rotation information here, and the same thing with the scaling keys down here. So that's it for that method. That's our info for anim data. So we got one last smaller debug section to add here. That's this additional reports. These are ones we could just kind of add extra inquiries that we might want. Here we just have a little message thing for creating root information, and what we're creating it for. Prep to build models tree, set up the models root node. We got this show mesh bone creation info, so we can pass in our Assimp mesh, our SkinModel skin mesh, whether or not we want to show the offset matrix information, and a mesh index. We show the Assimp mesh's name and the corresponding scene mesh index. We can next show the vertex count and the material name and that material's index and the bone count. We've got this note here too. If an imported model uses multiple materials, the import splits up the mesh and uses this value as an index into the scene's material list. So if, for example, you have maybe just one single mesh, but you got 3 different sections on it for different materials, each with their own properties and their own textures, this is just going to split it up like it's 3 different meshes, basically. That way, a material and texture switch can be done at the appropriate time when it's completed with all the polygons for that particular material. And we can loop through that mesh's bones with name, mesh index, and the bone index, the number of associated weighted vertices. And if we have matrix info set to true, it'll show the offset matrix for that bone. And that's for setting up that binding pose. So moving down, we have this show node tree info here. Got our tab level, our current Assimp node, whether or not we want to show matrix information, the SkinModel's model node, the SkinModel itself, and the scene. So this is just the usual tabbing based on what depth in the tree we're at. We got the current model's name, the Assimp node name that we're dealing with at the moment, and if in this node there are mesh indices, we'll say this node has mesh references, provide the count, mesh count, and here will be the list of the mesh indices. And then going through those, we show the node meshes with animated transforms, and we show them by name, so we're showing what the names of those are. And if we're saying we want to see the matrix, we can see the scale rotation transform of the current node. Here we just have to create this SRT info to string, and we'll add that into our extensions later, which will be another class in our SkinModel helpers. And then here we're looping through our scene meshes. So we need the index of the bone in this mesh, need that bone, and we're checking based on the model node's name of the current model node, which was passed up here. So here we're going to write out the node is also a mesh node. So this may be a node targeting a mesh transform with animations. We're going to do that if is a mesh node. Here we say we're adding the unique bone for the node, the model node name, the mesh, showing the index of however many meshes there are, and its name based on the current mesh index in this loop. And it's a bone in mesh number, mesh index, importers, bone index and mesh, and then we say what the adjusted bone index and mesh is, which we got here when we did this get bone for mesh. Some confusing diagnostics. So that get bone for mesh, we actually got that down here. Supplying the model skin mesh name we're looking for, we're going to output the bone and the bone index in the mesh. So we loop through our skin mesh's mesh bones and see if any of those match up to the name we're looking for. If so, we say true, and we output which bone it is. So we're referring to that model bone in our skin model. And we also return which bone index that is. And our last bit of debug information, got this show mesh info, passing in a mesh index, and we can show our scene mesh information. Face count, vertex count, normals, bone count, has animation attachments, material index, vertex color channels count, tangent count by tangent count, UV component count. So just some counts and some general information about that mesh in the scene. And that's it for this long and tedious, crazy debug information. Oh yes, I just remembered one last thing in our debug here. We're missing the extension for this, and we're missing the extension for this one here as well. So over to the right here, we've got our SkinModel helpers folder. I'm going to right click on it and add a class. This class will be named Loader Extensions. Loader Extensions. And again, just a reminder, this is based on Wil Motil's stuff. I added this using XNA equals Microsoft.xna.framework, so we can avoid any conflicts that way. We'll just use the XNA dot so that it knows what we're talking about. And again, I got the using Assimp up here. First, we'll change this to a public static class. We're going to have a region called additional info extensions. And the stuff under this region will probably only be used for debugging. So if we got a Assimp vector 3D, we can say dot to string, and then it will format the vector for output in our debug. So like I said, I wasn't the one who originally coded this. I can't tell you too much about how this works, but it appears to be padding everything. And we got the same deal here for quaternion with the 4 quaternion values, X, Y, Z, W. And if we want to display information about an Assimp matrix 4x4, we can say dot SRT info to string with this and supply how much tab spaces to use, and that's going to call this Q SRT info to string. So reporting the quaternion scale rotation transformation information by setting this to true, because in here we accept a boolean for show quaternions. The point of having this is we can just assume that we're showing it with quaternions. So first we check out the determinant. If it's okay, we go in here and we use this m.decompose. So that's built into the matrix 4x4, and we can get the scale, rotation, and translation. We're going to use a quaternion to Euler XYZ, which is down here, supplying a reference to that rotation, which we got here, and getting back the rotation angles for the X, Y, and Z. And that's the Assimp vector 3D rotation angles And then this rotation degrees, this is going to get all three of the rotation angles converted into degrees. And then if we are showing quaternions, we set our string using the tab spaces we received as quaternion with some padding of 20 and rotation to string. And this is where we use that quaternion version up here. So we're using this. And we add to that display string the translation right here, formatted. And if there's any irregular scaling, then we'll show all three of the scale values. Otherwise, we'll just show one of the scale values because they're all the same. And we'll also show the three rotations in degrees. And this will return that string, returning it to here, and this will return it. And then that information will be added on in our debug messages. As far as this quat to Euler XYZ, got this down here. And we just want to get an Assimp quaternion and convert it to a Assimp vector 3D. Apparently the math can be found here in this comment here, squaring the W, X, Y, and Z and adding them together. And if this is already normalized, that'll add up to 1. So we got this test rule where we go X times Y plus Z times W. And if that test value is greater than what should be unit right here, plus this, times this halving value. If it's greater than that, then singularity is at the north pole. So this is the calculation for that. Z is going to be 2 times arctangent of X and W. Y is going to be pi divided by 2, which is about 1.57. And that's 90 degrees, and X will be 0. And if our test is less than half of our unit value here, singularity is at the south pole, and so the calculation is going to be negative in the Z, so negative 2 times arctan 2 of X and W, and also negative that 90 degree value on the Y value. And otherwise, we do the calculation like this. I've only momentarily skimmed over the math for this, so if you want to check it out in more detail, if you want to pause this and copy it, there's this website too you can go to where you can look into more detail on this conversion. That's all we're going to add to extensions for now. We'll come back and add some more things later if we need to. Let's go back to our loader. So we may have to do a quick actions here using Game3D skin models, skin model helpers. And I got this little file options region in our skin model loader. The loading level preset, if it's 0, it targets real-time maximum quality. 1 targets real-time quality, 2 targets real-time fast, and 3, which is what I'm going to use, is set up to sort of squash down the meshes, and it's best suited for smolder models. So I based this originally on Wil's setup, but I think I modified it a bit, so it might not be exactly the same. We can set reverse vertex winding, which reverses the model's winding. Typically this will change the model's vertices to counterclockwise. In my case, I'm using clockwise. There's also add looping duration, and we have that right here. So that adds a tiny little bit of time on the end of the animation to support a smoother looping process. If your animation is set up properly for looping, then you don't need to worry about that. For the ones I tested, it doesn't seem to make any noticeable difference one way or the other. I do recommend going to the Assimp website, to this website here, and check out the property config stuff. We got this no skeleton mesh config set to true. That disables that dummy skeleton that's used to, it's sort of a mesh to show the skeleton for viewing purposes, and that's if it's actually in the file. I set the import cameras config to false. We'll just be using our own game cameras. There's a sort by primitive config, and here I have primitive type point and line, and I've commented it as primitive types we should remove. So you might want to look at that a little more. I'm guessing this just removes lines and points. Vertex bone weight limit configuration. We're allowing up to 4 weights per bone. It'll pick the 4 most significant weights. With this normal smoothing angle config 66, I'm telling it to smoothen out the vertex normals using a threshold of 66 degrees, which is supposed to be fairly ideal. My guess is if the angle of the surface is much more than 66 degrees, it's not going to contribute that normal as an average value for that vertex. Again, I'm not entirely sure about how it does the smoothing. I know how I do mine. Mine just averages all the surrounding polygons. So you might want to look into that and see what it's doing with this threshold angle. FBX strict mode config is set to false. Again, you may want to look into that. I'm not sure what that's for. Okay, I'm going to shrink these 2 regions because a lot of that's just extra options. So down below that, I've started this constructor region. Here we're just passing in the content manager, the graphics device, and we build a new load debug info. And we pass in this loader, so then it can reference it from inside the load debug info we made earlier. Down below our constructor, we got our set default options. Every once in a while, there may be a point where we got a group of animations that we may want to add extra loop duration onto to sort of pad the looping animation. Actually, I should relabel this set a debug texture. Added looping duration is public, so you could probably just directly select this public member and modify it in your code before loading that next animation. That is if you didn't want to set the debug texture also. So you probably only use this once. In fact, it may be that we might not even use it. I'll collapse the constructor and we'll go down under this. Next, we're going to add a load region. First, I'm going to start by showing you some of the overloads that we may want, and these are for loading the skin models, obviously. We can pass in a file name or a file path, so that's why it's labeled like that. And the loader's smart enough to kind of look for it, so that's why we could just pass in a file name if we want. Alternative directory, the effect that we want to use with this particular character. Optionally, we can rescale it, but by default it'll be scaled normally. So we'll just keep track of that alternate directory and go ahead and load using the file name that was passed in, the SkinFx, and the rescale. The next one is the same, except we have this boolean for using debug texture, which just tells it whether or not we should use that debug texture. This one, you may actually want to use it if you want to use one of these defaults up here, like for real-time maximum quality, real-time quality, real-time fast, or custom. Again, we're probably going to use custom, and you can set that loading level preset just by assigning the loading level preset right here, and then it just calls load again. Next, I added this load section. This is your main load method right here, which these overloads are using, and it just takes that file name, the skin effect to use with the model, and whether or not we're rescaling it, that's optional. In our case, we're probably going to rescale it because our model scene assets could be different sizes, characters could be different sizes, we might want to adjust the size. So this first region here, alter file path if needed. Some of this you may need to right click on and add the usings for those. If you want, you don't have to use this console.writeline, you could also use like debug.writeline and set it up for that. Doesn't really make much difference. Here we're just getting the file path name without the file extension, so if it's a PNG or whatever. If it's in our content folder, we're just going to use the regular content load, so we're not worried about the extension. And just so you're aware, that's going to be used for loading our textures for each material. So we set up a string that combines our current directory, environment directory, with content, and then that file path, the file name without the extension. So it could be a subfolder in content. For example, it could be something like this. If it couldn't find it, it'll check in the assets folder. If you have an assets folder, for example, you may add an assets folder on the right over here and add your FBXs that way, and then right click on it, change the properties to copy to. I'll show you that later too for adding the FBXs into your content and changing them so that they're copy to. Before I show you that, I'll show you what I originally had and what I was exporting. So as you can see here, I got some subtle normal maps on some of my materials here. For example, for the fabric and the shoes, and something for the eyes too. I think the eyes I could probably fix up better. This rim actually really shows up in the normal mapping. You only really notice it, I guess, though, if you're really close. What you'll notice is different this time from the other tutorials I did is I'm not consolidating the mesh. The consolidated version probably is a little bit more efficient, but in this case they are actually separate, and if I had wanted to do facial morph targets, that might make it a bit easier. Although I think I'd prefer to do bone animations to control everything in the face. So if I zoom in a bit, you can see the normal maps, although they are fairly subtle. If you change the viewing angle or the lighting angle, you can kind of see the change in the shading across the surface. You can even kind of see it in the tail a little bit. And if we scaled our bump mapping, it might make it a little bit more obvious. And now it'll be a lot easier to export our character. And just for those who are just starting on this type of tutorial, I'll just show you quickly how we do that. We double click on the root bone to get all the other bones, but I don't really want to export any of these spline helpers, so let's choose to select bones only from this menu over here. We'll click over here to deselect, and then double click on the root bone, and you can see that all the bones are selected. We'll go back up to our options for selection up here and change to geometry, and then zoom back, hold down Control. I'm going to use my other control because this one's not working right, and select everything. Now we should have only the geometry and the bones selected. We can go to File, Export, Export Selected, not regular export, but just selected. And I'm using this revised directory, and I'm going to export it as KidIdle. And the options I'm choosing: triangulate, convert dummies to bones, although I don't think that's going to matter. Animation selected, remove single key is selected. I'm going to change the end value to 199. I'll make sure to remember to do that for each one. Otherwise, you won't be able to blend the animations. Or I should say, you won't be able to blend them as easily. I have deselected morphs. See, cameras off, lights off. Embed media, I got it off for now. In the future, I might add embedded media support and then check that option. And instead of using content, we just use the embedded media. Otherwise, we're going to copy all our texture files over into the content folder in the kid directory. I'm using centimeters units, Y for up. In this case, I think we could use binary. I'm using ASCII again, just early on. Later, I might change it to binary. You might get warnings about turned edges. That doesn't matter. And it's pretty normal. Modifiers above skin. In our case, there's some flex modifiers. It's possible to eventually add our own vertex shader to take care of any kind of flexing. So everything's okay. And then we can copy a kid folder containing those files as well as the textures associated with them into that folder in our content directory. So now in the content folder, I got this kid folder and I got the textures and the FBX file here. And this time we don't actually have to tamper with any of the paths or anything. No modifications at all, we can just leave it as is. Then in content I can say add existing folder and add that folder. And its contents should all be here. For the KidIdle.fx, we're going to do something sneaky. We don't have a content writer, so we're just going to copy it directly into the content folder. So it has no processor, so the first thing we'll do is click on that file and look down in properties. For build action, change it to copy. Importer, go to processor actually, and for processor, click on no processing required. So it'll just ignore this importer part, but it'll copy it and it will not process it because we're going to load it ourselves directly. So then save and exit. Okay, so what's going on here is it's setting the string again to try out assets if it didn't find it in there. It probably already did find it though the very first time when it tried it in content, at least in our case. Otherwise, it's going to try it in the current local directory. If it can't find it there, then we're just going to notify the programmer that there's been a problem finding that file or path. So most likely by this point, we found the file and we can assign that new string to full file path. I'm going to go down a bit here. Here we're going to make a new Assimp context, which will act as our importer. We'll go through those configurations that we set up earlier. Up here, that's our list of configurations. And we'll tell the importer to set those configurations. And we'll tell it importer scale is equal to the rescale value that we passed in. In our case, we actually most likely will use the scale. All right, and down here, this is the part where we actually try to load the Assimp scene. Depending on the loading level preset, we'll import using one of those associated presets here. So target real-time, maximum quality, so on and so forth like we looked at before. We're probably going to use the custom one, which is this default here. So we're going to need to flip the UVs for it to look right. Join identical vertices, we'll get rid of any redundancies for our indexing. Triangulate is turned on as a precaution, although we had ensured triangulation in the export. But I guess just to be safe, we'll leave that. We'll find any invalid data and remove it, like incorrect normals. We're going to generate smooth normals, so recalculate those because there could be some bad ones. We're going to optimize it for cache locality. We'll fix any in-facing normals. And there's a comment here, doesn't work well with planes. Turn off if it goes dark. We'll calculate our tangent space, which is useful for normal mapping. I've had a couple times where the tangent information didn't seem right, so maybe to be safe, you could calculate your own, but it should work. Generate UV coordinates is mostly just for if something did not export any UV texture coordinates, then we can generate something for that. To be safe, we'll validate the data structure. find instances, set global scale, we'll set flip blinding order. That'll change counterclockwise to clockwise. If something is inside out, then if this is turned off, that would fix it. Just depends on your rasterizing setup, like it says here. There's some other possible post-process steps in the loading process that we might want. I've got these turned off right now because I don't think I'm going to use any of those. There's even other ones here that you might be able to take out. Not that it's really going to affect the load times. And if something goes wrong, we say problem reading file, what the file name is, and the message for that exception. And otherwise, at this point, everything's gone well. And we can return the new model by saying return create model, and we'll do the create model right under this, passing in that full file path that we got up here, and the skin effects to associate with this model.